Uh, Thank you to the organizers. It's really a pleasure to be here. My first time in Bangalore and second time in India. India is a special place to me, in part because it's where I first started thinking about many of the sandpile type questions that I'll be telling you about this week. I made my notes this morning. I had some big collection of notes, and then just this morning kind of ripped them out of the notebook and put them in a completely different order. So here's a somewhat whimsical table of contents for what I want to say today. So how's the visibility in the back? Should I write bigger or it's good? Okay, so these topics will gradually become more clear what they mean. Let me start with the year 2008. So to fit this into a personal story, I was a fresh PhD looking for some exciting travel adventures. So I head to India. I had a free semester for traveling, and after you see a certain number of palaces, forts, and temples, and so on, they all start to blur together, and you start, realizing, what's really important in your life is sandpiles. And fortunately, one of the world experts in sandpiles is Deepak Dar, who was at Mumbai at that time. So I went to visit Mumbai and speak with him and his students, and that started started me working on a topic that I hope I'll work on for many more decades. One reason I found sandpiles so interesting is that during PhD, I had worked on several related models and showed they all have the same scaling limit. And sandpiles, superficially looked a lot like these other three models, but they didn't have the same scaling limit. And in fact, at that time, we didn't know anything rigorously about their scaling limit. And that was kind of a mystery. I'll make these words more precise over the course of the lectures, but it fits into the topic of this week of universality, in that the other three models that I had studied, they all had universal scaling limits, and we'll see, in a sense, the Abelian sandpile model, although it has a scaling limit, has a lattice-dependent one. 2008 is important for another reason, in that, globally, that's when there was the big financial crisis. And that's somehow appropriate for talk on sandpiles, because the original motivation for sandpile models comes from Well, from back in the year 1987, is this famous paper of Bach, Tang, and Weissenfeld. And this is kind of my interpretation as a mathematician of what they wanted to say. So they asked, well, this question: why heavy tails? So you look around, and there are many systems in nature that have heavy-tailed random variables. You know, if you look at earthquakes, you look at stock market price movements, forest fires, and so on. Any kind of system that has sort of disaster events on all different scales seems to exhibit these heavy tails. And you know, you can look at this question and say, well, it's kind of a strange question. I mean, like, you know, there are many different probability distributions. Some of them have heavy tails. Why wouldn't you expect to see some in nature? But they had a particular reason why, you know, it's a little bit puzzling a priori that you should see so many heavy-tailed distributions in nature. And the reason was that when you sit down and make a model with some parameters, you typically find is that only for very special parameter values do heavy-tailed distributions come out. So somehow, you know, these natural systems, you know, what's the chance that they end up right at those finely tuned parameter values that create heavy-tailed distributions? That seems like an unlikely coincidence, and so they proposed this mechanism which they called self-organized criticality. So the criticality refers to the heavy-tailed distributions, and self-organized refers to some mechanism that the system has where even if initially it was in some other region of its parameter space, its dynamics would tend to drive it toward these special critical values where you do see the heavy-tailed distributions. And what they wanted to do, again, my interpretation as a mathematician, is come up with kind of one canonical model of this phenomenon. And the model they proposed is a pile of sand. So they said, imagine a pile of sand and sprinkling some additional grains of sand on top. So here's the pile, here's the sand getting sprinkled on top, and the parameter we can look at is the slope. So and then you want some observable. So you can observe, maybe it's hard to observe exactly where each individual sand grain is in the pile, but you can observe, you know, bigger macroscopic events, like when you drop a certain amount of sand, how much mass moves how far down the pile. So the kind of distributions you can look for are, you know, how big of an avalanche does dropping a little bit of sand on top cause, right? So when you drop this sand, you know, it will cause some sand that's already in the pile to kind of slide down. And there's some critical slope where you're going to observe power law distributions of these avalanche sizes. And the idea is that, well, if you started subcritical, so if you start below this critical slope, then you won't observe very many big avalanches because you won't have this heavy-tailed distribution. And as a result, you know, your sand should start to pile up more so that your slope will increase. So the very fact that you don't observe frequent big avalanches somehow makes this pile get steeper. And so you tend closer to zeta c. On the other hand, if you had some, extremely steep, unstable pile, and you drop just a little bit of sand, then, what would you expect to happen? Well, you'll get some massive, massive avalanche that flattens the pile out. So, in either direction, the dynamics of just dropping extra sand on this pile, no matter what you started the slope at, should tend to drive you towards the critical slope. That's their idea. So, so they proposed a kind of toy model of this situation, which goes by the name Abelian sandpile model. Okay, let me define the model, and then I'll get to the next item here, which is, well, what is it actually a model of? So it's not going to look very much like this cartoon picture, because, well, we have to make it math, right? So, we want to prove theorems about it. So, so it's going to live on some finite connected graph. And well, if you like, you won't lose very much by assuming this graph is like a piece of the square grid, okay? So example, it could be, a box in the square grid, okay? So and our sand grains are going to live on this graph. So let's say physicists will complain about this definition, but that's their right to do that. So a sandpile is a function S from the vertices to integers. So what you think about here is, S of vertex X is, number of sand grains at vertex X. And usually I'll call sand grains chips because it's easier to say. And, well, you notice I put Z here, so all the integers, including possibly negative integers. So, what do we really mean by a negative number of sand grains? You should think of that as a hole that can fill up with sand. So think of a hole of depth minus S of X. Okay, so why do I say physicists will complain about this? Well, this is one of many lessons I learned from Deepak. So I was writing an article years ago with Jim Propp, which we called What is a Sandpile? And supposed to be just a light introduction to the subject. And we sent the copy to Deepak's comments, and he chose to pick on this innocent-seeming definition with a very interesting comment. He said, well, this is like the microstate of a sandpile, okay? This is like, if you could see every little tiny detail, like exactly how many sand grains are in each place, then okay. But, from a physical point of view, you maybe can't see all that stuff. You can see rather macroscopic properties of the pile. What color it is, or how steep its slope is. So, good. So, since we're mathematicians, we're going to keep, be happy with viewing a sandpile as its microstate. And okay, what do you do with sandpiles? Well, you want to have some way that the sand grains can move around. So the simplest way to write down how they move, or at least the most useful way, is going to be to use the Laplacian. So let's write ZV for all the functions. Taking integer values on V. And the graph Laplacian acts on this space by, so I input a function f, and delta f is going to be another function, and that function's value at vertex x is the sum over neighbors of x of the difference in values between the neighbor and the value at x. Right, so I like integers because my sand grains don't, you can't split up a sand grain into smaller pieces. And so I want to keep my coefficients integers. So one nice thing about this normalization is if f is an integer valued function, then delta f is integer valued. It will no longer be true if I normalize. Maybe you prefer to think of this as a matrix, which is fine. So if you want to think of it as a V by V matrix, then well, it has two parts, right? So it has a diagonal part coming from this minus f of x term. So it has minus the degree along the diagonal. So degree of x is just the number of neighbors. This tilde symbol means x, y is an edge, or x and y are neighbors. And then it has a term coming from the neighbors, f of y, so that's like the adjacency matrix of the graph. So these A's are 1 if x and y are neighbors, and 0 otherwise. Okay, so it's some matrix you can associate to your graph, and it's useful for encoding how the chips move around in this model. Namely, so we say the vertex x is unstable if the number of chips there is at least as big as the degree. And toppling vertex x means redistributing chips according to a column of this Laplacian matrix. So means, if you like, replacing the sandpile S with S plus the X column of the Laplacian. So this little delta X is just a standard basis vector, so it's 1 if X equals Y, 0 otherwise. Okay, so far this is just a sort of notation-heavy way of writing something simple, but we're going to use the Laplacian so much that it's a useful way of introducing, of fixing our notation. So let's decode it. So what is delta delta X? Well, when Y equals X, I have this diagonal term, so minus the degree. When Y is a neighbor of X, I have a plus 1. And when Y is anything else, I have a 0. So if I add this function to S, what I'm doing is I'm taking away a bunch of chips at X, and I'm adding one chip at each neighbor of X. So if you want to write this in words, toppling X means send one chip along each edge incident to X. Okay, now when you do this, you might allow yourself to, you might create further unstable sites, and then you can topple them. And that's kind of the basic reason for choosing this, this setup, is you would like some kind of mathematical mechanism for an avalanche, right? So for dropping a sand grain, which then dislodges another sand grain, which kind of tumbles down and dislodges more. So you could see that sort of thing happening in the in this model. So let me do a simple example, which will also show this dichotomy, so between stabilizing and exploding. So in theorems, we're going to be interested in large graphs, typically, with sizes tending to infinity. But here's just an example on a small graph. So here's a 4-vertex graph, and here are my initial chips counts. So I have 2 chips at this upper left vertex, 4 chips at the upper right, 0 chip here, and I have minus 1 chip, or a hole of depth 1 at the lower right. These two are unstable because the degree up here is 2 and I have 2 chips, and the degree here is 3 and I have 4 chips. So either one of these is allowed to topple. And I haven't told you yet, how to decide in what order you should do the topplings. So it would seem that we have 2 options. So we can either topple this 2 first, and if you topple that 2, well, that's at a vertex of degree 2. So you're going to take away 2 chips from this site and add 1 chip to each of its neighbors. So the 2 would go down to a 0, the 4 would go up to a 5, this 0 would go up to a 1, and nothing happens in this corner. On the other hand, I could have toppled the 4 That's also unstable. And then it would send a chip to each of its 3 neighbors. So, and it would lose 3 chips. So the 4 would go down to 1, and the neighbors would each gain 1. And we're not done yet. So this is 2 possible first steps, but we still have to keep toppling. So this 5 is unstable. And so if I topple it, it'll go down to a 2, and everything else will gain 1. Or in my alternate history, the 3 is unstable, and if I topple it, then it will go down to a 1, and its neighbors will each gain 1. So you notice perhaps not surprisingly, although the intermediate states were different, both histories resulted in the same final stable sandpile. This guy is stable because at each site I have strictly less chips than the degree. Now, if you have too many chips, then it might not be so simple. So we say that this one is stable, meaning that S of x is strictly less than degree of x for all x. This one is not stable, but we say that it stabilizes. Because you can reach something stable with finitely many legal topplings. But some things don't stabilize. So for another example on the same graph, let's just rearrange these numbers by swapping the 1 and the 2. So to say we had 2, 2, and 1. Well, okay, this is no longer stable because this upper left vertex has 2 chips and degree 2. And moreover, if you topple it, you'll get this avalanche. So if you topple it, this 2 becomes a 3 down here. And so now you've destabilized this lower left corner. And then if you topple that, then you will destabilize the upper right corner. And if you topple that, you'll destabilize the lower right corner. And then if you topple that, then, then you'll have toppled each of the 4 vertices exactly once. And that means each vertex will have lost its degree many chips, but it will also have gained 1 chip from each neighbor. And so the net will be no gain or loss. So you'll end up back in the sandpile you started with. And so you'll just cycle through these 4 configurations forever. So this thing does not stabilize. You can't reach a stable configuration by topplings. Does not stabilize. And I want a more pithy way to say it does not stabilize, so I'll just say it explodes. So this is a dichotomy we're going to explore in various directions all week, is stabilizing versus exploding, and how to tell which is the case, and finding phase transitions between stabilizing and exploding. It turns out to be a surprisingly rich dichotomy. I mean, it's sort of like random walks are either recurrent or transient, right? And sometimes it's easy to decide which one. Sometimes it's difficult. It's a dichotomy of that sort. Okay. Let me pause for questions. So, is the basic model clear? Yes. Yeah, okay. So I didn't really say why I'm allowing my sandpiles to take negative values. So far, it's unimportant, and for many purposes, you don't care about having holes, and you may as well just have chips, and you don't need negative values. But for this, there's a theorem I'm aiming for as the goal of tomorrow's lecture, where negative values will be important. I'll say more about it tomorrow, why you need them. Other questions? So far I've done the year 2008, the year 1987, why heavy tails, Laplacian, and the dichotomy. Okay, but I skipped model of what? Okay, so it's the, there's a lot of models out there. It's a word everybody throws around. There's the Ising model, the Potts model, Edwards-Wilkinson model, et cetera, et cetera. But like, model of what? The simplest and least accurate answer would be to say it's a model of a pile of sand. And, well, there's any number of reasons why it's inaccurate. For starters, you could complain that, well, these pictures I drew, the pile is kind of higher in the middle and it's lower at the edge. And whether or not you're toppling, it shouldn't really depend on like the absolute height of the grain of sand, but rather on like locally what the slope looks like, right? So, we're calling these things sand grains or chips, but really, if we wanted to try to make this a model of a pile of sand, it would be more accurate to think of them as local slopes. So the idea would be, if you zoom in on a little piece of a pile and magnify it, then it will be rough, right? So it will have little places where it's steeper and places where it's less steep. And if you had a sand grain that's kind of sitting right at the edge of a very steep part, that would be the situation where it's unstable and it would topple. Okay? So if you want to really think of this as a pile of sand, you should think of chips as local slopes. That's the first comment. But there's all kinds of other reasons why you might suspect this isn't a good model of a pile of sand. And indeed, there are certain predictions you would make about these self-organized critical systems in nature, which this model doesn't seem to have. So the subject of tomorrow's lecture will be one particular example where we can rigorously see a difference between what these systems in nature ought to satisfy and what this model actually does. So, you might be tempted to, once you realize that actually it's not quite modeling what you originally wanted to model, you might be tempted to just throw it out and look elsewhere. And that's an understandable reaction. I sympathize with it. And so, in the last couple decades, there's been, although this was the original proposal of Bakhtaeng and Wiesenfeld, there's been a big proliferation of variants and other sandpile models, some of which are better candidates for the original pile of sand type of situation. On the other hand, this thing is a good model of a lot of other interesting phenomena, like, here's my list. Okay, so here's a partial list of things that you could model either with this Bakhtaeng-Wiesenfeld sandpile model or one of its relatives. So there's the original self-organized criticality motivation, which, kind of still comes with a question mark because there's not a lot of rigorous theorems backing it up, although, we're working on it. One thing I want to propose is, so self-organized criticality is kind of about disasters on all scales, like there are little avalanches and medium-sized avalanches and big system-spanning avalanches. What if you only care about the latter? So you only care about the big disasters. The 1929 stock market crash, or some giant earthquakes. The real, this disasters that are as big as the system itself. There's a lot to investigate about big disasters, and in one particular case, we can actually prove something about what the model predicts about big disasters. Then there are some completely different seeming applications. So depending on what kind of experiment you do, what kind of graph you do, where you start your chips, you can view this as a model of pattern formation. So if you start your chips in some simple deterministic configuration and stabilize them, you will often get these very intricate patterns. Another day I will bring in some simulations and show you what these patterns look like. They're remarkable for a few reasons. One is that they have what Ayyer has called proportionate growth. So, you can make a pattern of any size by, if you wanted a pattern of a certain size, you can start with an initial condition of an appropriate size. And then if you start with a bigger condition by, adding more chips, the whole pattern will kind of reform on a larger scale. And, there are natural systems that behave like this. If you think of an animal as it develops, all of its organs and its internal structure somehow grows in proportion to the whole thing. And interesting to think about, how do the individual cells in the body somehow coordinate locally to cause this global proportionate growth. Another interesting thing about these patterns, which, well, it will be more vivid when I show you the picture, is there are many different patterns that occur in different places, sometimes in predictable places. And so it's a good model of kind of why is our universe so heterogeneous? So, why is there air in this patch of the universe, and there's, wood in that patch over there, and there's, a lot of interesting stuff going on in Vladis's brain. There are different things going on in different places. Yet, the laws of physics aren't different in any of those places. So, how is it that happens? We're so used to it, we don't think of it as remarkable, but it kind of is when you think about it. So you got to ask for what's the simplest mathematical model of a system that does this? So it has only one law of physics, right? It's this law about if you have at least as many chips as your degree, then you topple, sending a chip to each neighbor. And then you can work in some very symmetric universe, like Z2 or ZD. And so you've got the same law of physics everywhere, and you take some very simple initial condition, like n chips at a single site, where n is some very large number. And then you can stabilize it by topplings, and you'll get this kind of wild picture, which is composed of patches with a sort of distinct pattern in each patch. And you can classify these patterns. There's a countable family of them, and they're in predictable places. So there's, a patch of this universe with a certain periodic pattern of sand, and there's another patch with a different periodic pattern, and so on. So I think it's intriguing as a model of that. And then, so two other things I would add to this list are synchronization. So, how there's this kind of general phenomenon that my Cornell colleague Steven Strogatz wrote a popular science book about. It's called Sync, where any kind of system of coupled oscillators, depending on the strength of the coupling and the geometry of how the oscillators are coupled, will often tend to synchronize, so that even if in the beginning the oscillators are out of phase, if you run it long enough, they'll all be in phase. With the right update rule, you can think of this sandpile as a basic model of this. And the last, maybe unexpected item here is computation. So you can think of your graph with its chips as some sort of computing device. Maybe some of the nodes are input and some of the nodes are output, and the rest is sort of internal to the computer. And you could send some chips into the device, and there's a bunch of topplings going on, and then it spits out some chips at the output nodes. You can ask, well, like, what kinds of things can you compute with a device like this? And I mean, that seems like a kind of bizarre question, but it turns out to be a fascinating and fruitful direction. Okay, so enough of the philosophy for now. So it's a model of various interesting things. And I guess another thing that's independent of this list is, even if you think it's not a model of anything interesting, it leads to a lot of deep questions in pure math, which is, for many of us, a good reason to study it, all for its own sake. Okay, the remaining items are two Markov chains and delta rho. Okay, so let me do delta rho first. Okay, so a good way to vary your model is to, if you go to the very heart of it, the Laplacian is kind of the most important ingredient of your model. So, for example, in these other stochastic sandpile models that followed, you change your toppling rule so that, instead of just adding this kind of vector, this deterministic vector, you would send your chips somehow in random directions. And there are many ways to do that. You get many different models this way. You'll hear about some of them later in the week. So the point I want to make is that you can capture all that variety and even more if you're willing to accept a very broad notion of what a Laplacian is allowed to be. Okay, like this Laplacian, it's a very nice thing. Like, it's a linear operator. It's even an integer valued linear operator. So that's great. And that enables us to prove a lot of things about it and compute with it, whereas we can't compute as well with these other models. But I think it's useful to phrase them all in terms of Laplacians. And the way you can do that is, so there's a device that everyone who's worked in this area knows about, but it can be a little subtle to use it the right way. So even if you know about stacks, I want you to rethink them because there are different ways to phrase your model in terms of stacks. So, okay, so what are stacks? Stacks are some instructions that you specify in advance. If your model is random, you could think of them as some quenched randomness that some coins you flipped in advance. Okay? And so mathematically, they're a map from the vertices of your graph across the non-negative integers to the vertices. And you think of, so rho of a vertex x and an integer n is some vertex y. So this thing means that, if, or whatever your model is doing, the nth chip emitted from x goes to y. Now that doesn't fully specify the model because we haven't said, like, when is it legal to actually emit chips, okay? So to complete the specification of the model, we should also say something about, which moves are legal, legality. So, and that's specified by a function v cross n to n. And what that encodes is, so this should be a monotone increasing in the n coordinate. And that tells you how many chips you're allowed to emit. So eta of x n equals m. So this means if you receive a total of n chips, then you emit a total of m chips. Then emit a total of m chips. So here's something which, for the experts who are bored with the ordinary Laplacian, what I invite you to think about is take your favorite stochastic model. It could be activated random walkers or the Abelian monomodel or the Oslo model, any of these. And just as an exercise, say what rho and eta will give you that model. And another exercise for the experts is show that all of these models are Abelian. So the only thing you need, rho can be anything, and eta need only be increasing. So it gives a big family of kind of potential models to work with. And I wrote for myself on the plane ride over here all the models I know about. I made a big chart of what's the rho and what's the eta. And when you make that chart, you kind of realize how much unexplored territory there is. All the models that are in my chart, like the rho and eta, have some very non-generic properties. Like, for example, in all those models, rho and eta are independent of each other. And eta is within bounded distance of the identity, in its n coordinate. And, some other non-generic properties. So if you look at eta, let's say you receive a chip and you're wondering, does that mean I'm supposed to emit some chips? And if so, where am I supposed to emit them? Well, first you look at eta and you say, okay, so far I received n chips, But now I received another one, and so I have to compare eta n to eta n plus 1, right? And that difference will be a non-negative integer, which will tell me how many chips I have to emit. Then, to decide where to emit them, I go up to rho, and I say, okay, I've already used the first m stack elements at that vertex, and I know how many more of them I have to use. So I know, how many chips to emit to each neighbor. So you don't need to label the chips in order to implement this. Good, okay, yeah. So what are rho and eta for the Abelian sandpile model? Rho is periodic. So there's no quenched randomness in the model, right? Because topplings are deterministic. So it just cycles through the neighbors of x. So it's periodic mod degree of x. And eta is, well, if I receive n chips, how many am I supposed to emit? I should emit n times floor of, degree times floor of n over degree. Right, so every time I receive a batch of degree chips, I emit degree of them. So these choices give Abelian sandpile. So notice some details are irrelevant, like I didn't tell you which order to take the neighbors in this periodic sequence, but because of the choice of eta, it doesn't matter, because I always emit my chips in batches of degree at a time, and then I do a full period, and so each neighbor gets one. Okay, I can see this this stack Laplacian caused some minor confusion. So let me say that this was mostly an aside to keep the experts from falling asleep, and I'll come back to it and clarify it when it becomes relevant. But everything else today and tomorrow won't use the stack Laplacian, and if the experts fall asleep, later on today or tomorrow, they can always wake themselves up by trying to replace the ordinary Laplacian by the stack Laplacian in any of the arguments. I guess the last thing I'll say about stack Laplacian is it gives you a kind of framework for proofs. So many proofs have the flavor that if you have a large function, then the stack Laplacian I didn't write down the definition of stack Laplacian yet. Yeah. Is close to the real Laplacian, to ordinary Laplacian with high probability. So there are many kind of proofs of this flavor. So let me conclude the aside about stack Laplacian by just writing down for you how it's defined. What is U? U is a function. So here's the definition of this object delta rho. So the stack Laplacian delta rho it takes as input a non-negative integer valued function on the vertices, and it gives you an integer valued function as output, possibly negative, and it's defined as, so u is the input function. It's defined by seeing how many chips would you receive and how many chips would you emit if you use this portion u of the stacks. So what you get if you write that in symbols is, it's this, first you do the receive chips, so that's the sum for all neighbors of the sum, say j equals 1 to u of the neighbor of the indicator that the stack at that neighbor y points to your desired vertex x, yj equals x. So this total thing is like counting chips received. Right? And then you subtract off chips emitted. So as an example, take your rows to be IID uniform random neighbors, so instead of periodic. Then, well, the stack Laplacian is now a random function, but imagine you plug into it a very large function u, a function taking large integer values. Then, well, you have you have various statements of this form, right? Saying, well, approximately the same number of stack elements point to each neighbor. And, well, if it were exactly the same number, it would reduce to the ordinary Laplacian. Since it's not exactly the same, it's still random, but it's close. Of course, depending on the model you're working with, you have to quantify, and the application you want, you have to quantify large, close, and high probability. But it gives you a kind of template for what you're often trying to do. Okay, so back to stuff that should be understandable with no background. So back to the ordinary Laplacian. Right, I want to tell you the two Markov chains, except it's 11. So, okay, so we can stop and do some discussion, and I'll tell you the two Markov chains and the least action principle on Tuesday, later this week, but good place to stop.